Hi, this is Tom. Welcome to my channel. I'd like to talk about a concept of visualizing mathematical proofs for real analysis using open covers. And um, hopefully this will become clear as I go through this, but I find this a very fun thing to do, is to have a geometrical visualization that you can translate to a rigorous proof. So this is an illustration of the Bolzano-Weierstrass theorem. What we're going to do is for each point on the line, we have a ball of size epsilon. And because the set is compact, we can replace any open cover with a finite subcover. So we have a finite number of balls, and all of the balls have radius epsilon. Now, a sequence has an infinite number of points, but we have a finite number of balls, so at least one of the balls has to have an infinite number of points, all of which are within epsilon, and that's exactly the definition of a convergent sequence. So we have a convergent subsequence because at least one of the balls has an infinite number of points. Now, it's possible that more than one ball has an infinite number of points, but Bolzano-Weierstrass says that there's at least one convergent subsequence. Okay, now let's look at Cauchy. Cauchy criterion. So the Cauchy criterion says that for m and n greater than big N, there's some n large enough that all the points of the tail of the sequence are within epsilon of one another. That's what this is calling an infinite tail knot. So from the first part of the proof is the same as Bolzano-Weierstrass. We know we've got a finite number of balls. All of them are within epsilon of the possible accumulation point. One of them has to actually be an accumulation point because we have an infinite number of points. We have to get into a finite number of balls. So from Bolzano-Weierstrass, there is at least one convergent subsequence. But when we add the Cauchy criterion, they all have to be, all the infinite points of the tail have to be within at most one ball, because all the points are, once you get to a large enough n, are within epsilon of one another. So we have at least one ball from Bolzano-Weierstrass and at most one ball from Cauchy. And so that means that the sequence as a whole converges. And that's a way of visualizing that. Next, we'll look at monotone convergent theorem. And here we'll assume that the sequence is monotone increasing. Now, unfortunately, the visualization here isn't exactly correct. But the adjustment to make is assume that this point here is fixed, the left-hand point for all of the balls. So the first ball, and this could actually be negative infinity. So the first ball is okay, but the second ball should go from where I'm pointing to here. And the third ball should go from the left-hand point to here, and so forth. So each subsequent ball is eating all of the former balls. And we go like that to the end, and we append one ball of size epsilon that captures the supremum of the set. So because the set is compact, we can replace this with two open balls, which, and again, this isn't exactly right, but close. This boundary should actually be overlapping the green ball. Then we have the right representation. So the balls are all leading one another. Because it's compact, there's a finite subcover. So we have to have a case where we have just two balls that cover the whole set. And this ball, it overlaps here. It goes up to n, for some n that's large enough. And then we have a ball that covers all of an infinite number of points above n, which is, again, exactly the definition of a convergent sequence. So let me go back, because I can't remember if I made that point clear. The idea is that we have one ball, at least for boson wire stress, that has an infinite number of points that is within epsilon. And that corresponds exactly to the definition of convergence. And we have that again with Cauchy, and then we have that again with the monotone convergence theorem. So I like this concept very much, that if we can get an infinite number of points within a ball of where the radius is epsilon, that corresponds exactly to the definition of convergence. And then look at one more here that has a slightly different idea, and because I couldn't get the diagram to be correct, I'll just try to do this as quickly as possible. But imagine that these open balls this is the real number line, that the real number line should be down here. So each of the points has an open ball that's replaced with a finite subcover. All of these are of radius delta, such that delta forces the range to be within epsilon. And the idea is that we're assuming for contradiction that there's some value, that there isn't a C in our compact range that is mapping to our supremum, we could call S. And because we can replace it with the finite subcover, we can get an actual maximum as opposed to something that's telescoping, arbitrarily close to S. We can get an actual maximum that is disjoint from S. The idea is that if there's no C in our domain that maps to S, then there's some distance, epsilon, between that and where it actually maps to. And with the finite subcover, we can get an actual maximum that's disjoint and create a contradiction that way. Hopefully that was clear enough. But what I wanted to get to is that you can form a visualization in your mind using the open covers. And that's what I like to do. I find that to be a lot of fun. And I'll look at one last one, which is the intermediate value theorem. And here, in addition to compactness, we're going to add connectedness. So we start with a connected set in our domain, and we'll use the interval, the closed interval AB. And we'll form a contradiction by assuming for contradiction that there's some value, say L, that has no C in the domain that can be mapped to it. And that creates disjointed open sets in the range. And because the definition of continuity in a compact set is that you can map open sets in the range to the domain, we wind up with the domain being consisting of two open sets that are disjoint. And that's the definition of disconnectedness, which provides a contradiction. So that means there has to be a C that in the domain that maps to the range. So hopefully this is clear enough to illustrate the concept, which is, and of course I'm assuming that the viewer of this video is familiar with the actual sequence proofs. and I'm just coming up with compact variations using open covers that can be visualized. And that's something that I find very helpful in trying to understand the proofs, is if I can come up with a geometric visualization in my mind's eye that I can go back and forth from, the rigorous proof to the visualization. I find that a very helpful concept. You can come up with, tools that you can use. You can picture visually and then map that back to the rigorous proof in symbols. Well, I hope that was interesting, and thank you for watching. Until next time.